Have you ever wondered what happens to stars when they die? The night sky is a vast and mysterious canvas, adorned with twinkling stars of various sizes and colors. These celestial objects, fueled by nuclear fusion in their cores, illuminate the universe with their radiant glow. But like all things in the cosmos, stars have a life cycle, and their demise can be just as captivating as their birth. Among the many stellar remnants that populate the universe, white dwarfs stand out as fascinating objects of study. These stellar corpses, remnants of stars similar in size to our Sun, offer a glimpse into the afterlife of stars and provide valuable insights into the evolution of the cosmos. White dwarfs are incredibly dense and hot, their tiny forms harboring the remnants of once mighty stars. Imagine a sphere roughly the size of Earth, yet containing a mass comparable to that of our Sun. That's the extraordinary density of a white dwarf, a testament to the immense forces at play during a star's final act. These stellar remnants, though faint, emit a gentle white glow, a testament to the residual heat from their former glory. The journey to becoming a white dwarf is a long and arduous one, a cosmic ballet that spans billions of years. It all begins with the birth of a star, a magnificent event that occurs within vast clouds of gas and dust known as nebulae. Within these stellar nurseries, gravity draws together particles of hydrogen and helium, causing them to clump together and heat up. As the core of this protostar continues to contract and heat up, a critical threshold is reached, the ignition of nuclear fusion. At this moment, the star is officially born, its core ablaze with the energy released from the fusion of hydrogen atoms into helium. This nuclear reaction, akin to a controlled hydrogen bomb, powers the star for the majority of its life, a period known as the main sequence. Our Sun, a yellow dwarf star, currently resides in its main sequence, steadily converting hydrogen to helium and radiating energy into space. For billions of years it will continue this process, providing light and warmth to our solar system. However, even the vast reserves of hydrogen fuel within a star's core are finite. As the hydrogen fuel depletes, the star's core contracts further, its temperature and pressure soaring to unimaginable levels. This triggers the next stage in the star's evolution, pushing it off the main sequence and setting it on a path toward its ultimate fate. As the star's core exhausts its hydrogen fuel, it begins to fuse helium into heavier elements such as carbon and oxygen. This process releases even more energy, causing the star's outer layers to expand dramatically. The star transforms into a red giant, a bloated behemoth engulfing its inner planets and casting a reddish hue across the cosmos. For stars like our Sun, this expansion marks the beginning of the end. The outer layers of the red giant, loosely bound by the star's weakening gravity, eventually drift off into space, forming a beautiful expanding shell of gas and dust, known as a planetary nebula. These ethereal structures, illuminated by the dying star at their center, showcase the intricate beauty of stellar death. At the heart of this cosmic spectacle lies the star's exposed core, incredibly dense and hot. This remnant, no longer supported by nuclear fusion, collapses under its own gravity, squeezing its matter into an incredibly small volume. The result is a white dwarf, a stellar ember marking the final stage of a star's life. White dwarfs are truly extraordinary objects, defying our everyday understanding of matter. Imagine cramming the mass of the Sun into a sphere the size of Earth. That's the extreme density of a white dwarf. A teaspoonful of white dwarf material would weigh several tons on Earth. The temperature of a white dwarf is equally impressive, reaching tens of thousands of degrees Fahrenheit. This intense heat is a residual effect of the star's former life, the leftover energy from its core collapse. However, despite their high temperatures, white dwarfs are incredibly faint. This faintness is due to their small size. With a surface area millions of times smaller than the Sun, white dwarfs have a limited surface area from which to radiate their heat and light. As a result, they glow with a faint white light, slowly cooling over billions of years. Section 5: White Dwarfs in Binary Systems, Cosmic Dances, and Explosions. While many white dwarfs exist in isolation, some are found in binary systems, locked in a gravitational dance with a companion star. In these systems, the white dwarf's intense gravity can pull material from its companion, forming an accretion disk of swirling gas and dust. This accretion process can lead to dramatic events. As material from the companion star falls onto the surface of the white dwarf, it can trigger thermonuclear explosions known as novas. These explosions release tremendous amounts of energy, causing the white dwarf to brighten dramatically for a short period. In some cases, the accretion process can have even more catastrophic consequences. If the white dwarf accretes enough mass from its companion, it can reach a critical limit known as the Chandrasekhar limit. Beyond this limit, the white dwarf becomes unstable and undergoes a runaway thermonuclear explosion, resulting in a Type Ia supernova. Section 6. The Future of White Dwarfs, Fading Embers in the Cosmic Tapestry. As white dwarfs continue to radiate their residual heat into space, they slowly cool and fade over billions of years. This cooling process is incredibly slow, a testament to the extreme density and thermal inertia of these stellar remnants. Over time, the white dwarf will continue to cool and dim, eventually becoming a black dwarf. Black dwarfs are hypothetical objects, as the universe is not old enough for any white dwarfs to have cooled to this state. They represent the final stage in the evolution of a white dwarf, a cold, dark remnant of a once luminous star. These objects, if they exist, would be incredibly difficult to detect, as they emit no light or heat. The fate of white dwarfs in binary systems can be more eventful. Depending on the mass of the companion star and the distance between the two objects, the white dwarf may continue to accrete material, potentially leading to further novas or even a Type Ia supernova. Alternatively, the two stars may spiral closer together, eventually merging in a cataclysmic explosion. Section 7. Cosmic Chronometers Unraveling the Age of the Universe. White dwarfs play a crucial role in our understanding of the universe's age. By studying the cooling rates of these stellar remnants, astronomers can estimate the age of star clusters and galaxies. This method, known as white dwarf cosmochronology, provides an independent way to measure the age of the universe. The basic principle behind white dwarf cosmochronology is simple: the older a white dwarf, the cooler it will be. By measuring the temperatures and luminosities of white dwarfs in a given population, astronomers can determine how long these objects have been cooling, and therefore the age of the system they belong to. This method has been used to estimate the age of our galaxy, the Milky Way, to be around 13 billion years old, consistent with other age estimates based on different methods. White dwarf cosmochronology provides a valuable tool for probing the early universe and understanding the formation and evolution of galaxies. Section 8. White dwarfs and the expanding universe, clues to cosmic evolution. White dwarfs also provide clues about the expansion of the universe. Type Ia supernovas, which occur when a white dwarf exceeds the Chandrasekhar limit, are incredibly luminous events that can be observed from billions of light-years away. These standard candles allow astronomers to measure distances across the cosmos. By observing the redshift of light from these supernovae, astronomers can determine how fast they are moving away from us, providing evidence for the expansion of the universe. Moreover, by studying the properties of Type Ia supernovae in distant galaxies, astronomers can probe the expansion history of the universe. This research has led to the discovery that the expansion of the universe is accelerating, driven by a mysterious force known as dark energy. Section 9. Conclusion. White dwarfs, windows into the cosmos. White dwarfs, once thought to be insignificant stellar remnants, have emerged as vital tools for understanding the universe. These objects provide insights into the life cycle of stars, the evolution of galaxies, and the fundamental properties of the cosmos. As we continue to explore the universe, white dwarfs will undoubtedly continue to surprise and challenge our understanding of the cosmos. These stellar remnants, once thought to be the end of the story, have become windows into the vast and mysterious tapestry of the universe. Through their study, we gain a deeper appreciation for the intricate processes that govern the cosmos, and our place within it.